Okay, so another conclusion that we can have from the theorem that we saw before is, suppose f, a function f, if it is continuous in the interval and its Fourier series converges absolutely. That is to say, okay, so that the sum here, k, is equal k that goes from minus infinity to infinity of the absolute value of fk. Okay, so if f is continuous and its Fourier series converges absolutely, its Fourier series let's put it, converges uniformly. That is to say that the limit when n goes to infinity, the Sn fx f of x, the limit, this is uniformly in x. So we are asking to the function to be absolutely convergent. So not all functions are going to have a Fourier series that is convergent, so we will have to know which conditions will be enough to have an absolute convergence, and so that we can express the function as a Fourier series. Okay, so another conclusion that we can take from the first theorem, it's, suppose that f is 2 times differentiable, continuous differentiable, so its Fourier coefficient will be go 1 over absolute value of k squared when absolute value of k goes to infinity. So this will tell us that the Fourier series of f will converge absolutely and uniformly. So the function is going to have a Fourier series representation. And okay, so now I'm going to demonstrate this. Okay, so let's suppose that k is not 0. Okay, and let's recall if k was equal to 1 over 2 pi the integral minus pi pi fx e minus I k x, and I will already settle that k is not equal to 0. So, well, I will put the 2 pi here. So now, if we use integration by parts, we can say that the right hand is going to be 1 ik, it comes from this part, and now we will have the integral of minus pi pi f prime x e minus ikx dx. Okay, so after doing integration by parts, we will have this. So if we apply it again, we will have 1 over ik squared integral minus pi. Now f prime prime e minus ikx dx. Okay, so this is after doing 2 times integration by parts. Okay, so considering that we have this, and so now we can say that the Fourier coefficient fk is equal to 1 with the minus because it is an I squared, k squared, and f prime prime k coefficient. The 2 pi is going to cancel with 2 pi that is here, and so we have this equality. Okay, so we obtain a representation of the Fourier coefficient that has 1 over k squared, so that when if k goes to infinity, this goes to 0 with speed 1 over k squared. Okay, so the case where k is equal to 0, I'm not going to do it, but this will be equal to 0, so this will not be here, and we have to make a similar thing, but only considering f of x. So during the demonstration, we establish one of the most important properties of Fourier transform. So we haven't talked about Fourier transform, but we will know about it is that the Fourier coefficient derivative prime is equal to ik multiplied by the Fourier coefficient. It will be a property of the Fourier transform. Okay, so this will be um, for all k integer. Okay, and another remark is that suppose f is differentiable and we express f as a sum akx, then we could express f prime also as a sum, but this sum is going to be ak ikx. So we can express the derivatives of f in terms also of a series, and also in the same way, if we can express, we have an f that is 2 times differentiable, then we can express the function also as a sum. Okay, and this can be done for any quantity of derivatives.